An angle is simply how much you turn. Imagine you are standing on a line and you spin around to face a new direction. That spin is an angle. We measure that turn in two common ways. The one you probably know is degrees, where a full spin is 360 degrees. The other way is called radians, where a full spin is about 6.28, or exactly 2 pi. Now, the unit circle is a special circle we draw to make angles easy to work with. It is just a circle with a radius of exactly 1 unit. That radius 1 idea is what makes it so powerful, because it turns the circle into a measuring tool. On the screen, you can see a radius arrow rotating around the unit circle, tracing out an angle as it goes. So why do we even bother with radians and this unit circle? The big reason is that radians connect an angle directly to the distance traveled along the edge. If you walk along the unit circle through an angle of 1 radian, the path you walk is exactly 1 radius long. That simple link, angle equals arc length, makes all the formulas in calculus much cleaner. The unit circle also gives us a perfect grid. Because the radius is 1, the x and y coordinates of any point on the circle are just the cosine and sine of that angle. This turns tricky triangle problems into simple coordinate problems. In calculus, when we take derivatives of sine and cosine, the formulas only stay neat and free of extra constants if we measure in radians. Degrees would leave messy conversion factors everywhere. Let's build the radian from scratch. The word radian is a blend of a radius and an angle. Its definition is beautifully simple. Take the length of the arc you traveled along the circle and divide it by the radius. On the unit circle, the radius is 1, so the angle in radians is exactly the arc length. That is why a full circle, whose circumference is 2 pi r, gives an angle of 2 pi radians. The r cancels out. Half a turn is pi radians, and a quarter turn is pi over 2 radians. Now, the unit circle's real magic. Drop a shadow from the tip of the rotating radius straight down to the x-axis. That shadow's length is the x-coordinate, which we call cosine theta. Drop another shadow across to the y-axis, and that length is the y-coordinate, which we call sine theta. The radius, the vertical shadow, and the horizontal shadow form a right triangle inside the circle. Let's put this to work with a real problem. You stand 50 meters from a tall tree. You measure the angle from the ground up to the top of the tree and find it is 60 degrees. How tall is the tree? First, we convert that angle to radians because the unit circle works in radians. 60 degrees is pi over 3 radians. On the unit circle, at pi over 3, the coordinates are 1/2 for cosine and √3 over 2 for sine. The tree problem forms a right triangle where the height is the opposite side and your distance of 50 meters is the adjacent side. The ratio of opposite to adjacent is sine over cosine, which we call tangent. So tangent of pi over 3 is √3 over 2 divided by 1/2, which simplifies to √3, about 1.732. The tree's height is the adjacent distance multiplied by this tangent ratio. Imagine taking the unit circle we already know and unrolling it like a scroll. The angle theta, which was just a turn around the circle, now becomes a distance along a straight horizontal line. As we walk along this line, we look up at the height of a point that is tracing out a pattern. That height is the sine, cosine, or tangent value for that angle. So the graph is simply a picture that shows, for every angle, what the ratio equals. It turns a spinning motion into a wavy shape we can read left to right. In calculus, we are always asking how fast is this changing, or what is the total accumulation. A spinning circle is hard to measure directly, but a graph gives us a shape we can work with. We can draw a tangent line to find the slope at any point, which is the derivative. We can shade the area under the curve, which is the integral. And because sine and cosine graphs are the basic building blocks of every wave, sound waves, light waves, the vibration of a guitar string, understanding their shape is the first step to analyzing all those real-world rhythms with calculus. Let's build the sine graph from scratch. On the unit circle, sine is the height of the point above the horizontal line. As the angle increases from 0, that height grows, reaches a maximum of 1 at a quarter turn, shrinks back to 0 at a half turn, goes negative to -1, and returns to 0. If we plot that height against the unrolled angle, we get a smooth, repeating wave that goes up and down forever. The cosine graph is exactly the same wave, but it starts at 1 because at 0 angle the horizontal shadow is at its fullest. The tangent graph is trickier. Tangent is the slope of the radius line, the height divided by the horizontal reach. When the radius points straight up, the horizontal reach is 0, so the slope becomes infinitely steep. That creates a vertical break in the graph, called an asymptote, and the pattern repeats every half turn. Let's use the sine graph to solve a concrete problem. Picture a Ferris wheel with a radius of 9 meters, and its axle is 10 meters above the ground. Your height above ground as you ride is the axle height plus the vertical part of the wheel's motion. That vertical part is exactly the sine of the turning angle times the radius. So your height is 10 plus 9 times sine theta. The ride takes 4 minutes for a full turn, which is 2 pi radians. At 1 minute, you have completed a quarter of the turn, so theta is pi over 2 radians. The sine of pi over 2 is 1, so your height is 10 plus 9 times 1, which is 19 meters. That is the very top of the wheel. The graph of this equation would show you rising and falling in a smooth wave, exactly matching the ride. You already know sine, cosine, and tangent from the unit circle. Now, what if I told you these three are not strangers, they are deeply connected by a few simple equations that are always true, no matter what angle you pick? These are called the fundamental trigonometric identities. Think of them as a family tree, they show how sine, cosine, and tangent are related to each other. The most famous one is the Pythagorean identity, sine squared theta plus cosine squared theta equals 1. It comes straight from the unit circle, and it is the root of all the others. We will also meet the tangent identity, which links tangent to sine and cosine, and the reciprocal identities, which introduce 3 new family members, secant, cosecant, and cotangent. Why do we even care about these identities? Imagine you are facing a huge, messy expression in a calculus problem, something like sine theta over cosine theta, or 1 minus sine squared theta. Without identities, you might be stuck. But with them, you can swap that messy part for something much simpler. For example, sine over cosine is just tangent. And 1 minus sine squared is just cosine squared. Identities are your secret weapon for rewriting trigonometric expressions into forms that are easier to differentiate, integrate, or solve. They are the basic tools that let you reshape a problem until it becomes manageable. In calculus, you will constantly use them to turn a hard problem into an easy one. Let us derive these from the unit circle you already know. Take any point on the circle at angle theta. Its coordinates are cosine theta and sine theta. The distance from the origin to that point is always 1, because it is a unit circle. By the Pythagorean theorem, x squared plus y squared equals radius squared. So cosine squared theta plus sine squared theta equals 1. That is the Pythagorean identity, it is just the circle's equation. Next, the tangent identity. On the circle, tangent is the slope of the radius line, rise over run, which is sine theta over cosine theta. So tangent equals sine over cosine. Finally, the reciprocal identities. We define secant as 1 over cosine, cosecant as 1 over sine, and cotangent as 1 over tangent, or cosine over sine. These names come from Latin. Secant means cutting, because it cuts the circle, and cosecant is the complementary secant. Let us use the Pythagorean identity to solve a concrete problem. Suppose you are working on a calculus derivative and you see the expression 1 minus sine squared of pi over 6. That looks a bit messy. But the identity tells us 1 minus sine squared theta is exactly cosine squared theta. So we can rewrite it as cosine squared of pi over 6. Now, from the unit circle, cosine of pi over 6 is root 3 over 2. Square that, and you get 3/4. So the whole expression simplifies to 3/4. We turned a subtraction and a square into a single, clean number. This trick works for any angle. Whenever you see 1 minus sine squared, or 1 minus cosine squared, you can swap it for the other function squared. That is the power of identities. They give you a library of replacements to make your math life easier. Imagine you know a right triangle's opposite side is half as long as its hypotenuse, so the sine ratio is 1/2. You want the angle itself. An inverse trigonometric function is the tool that undoes the sine, cosine, or tangent. It takes a ratio and gives you back the angle that produced it. For example, if sine of theta equals x, then the inverse sine of x equals theta. We write it as arcsine, meaning the arc whose sine is x, or with a little -1, like sine inverse. It's the reverse question, not a what's the ratio, but which angle. In real problems, you often know the sides but need the angle. A ladder leaning against a wall makes a shadow on the ground. You can measure the shadow and the ladder's length, giving you the cosine of the angle. To find the angle itself, you need the inverse cosine. In calculus, when you see something like the square root of 1 minus x squared, a clever substitution is to let x equal sine theta. Then you need inverse sine to switch back to theta. Inverse trig functions are the bridge from ratios back to angles, and without them, you can't solve for the angle in geometry, physics, or advanced integration. A trig function like sine takes an angle and gives a ratio, but many angles give the same sine. Sine of 30 degrees and sine of 150 degrees are both 0.5. To make an inverse that's a proper function, we must restrict the original sine to a piece where every ratio comes from exactly one angle. For sine, we keep angles from -90 to +90 degrees, where it climbs steadily from -1 to 1. The angle we get back is called the principal value. For cosine, we use 0 to 180 degrees. For tangent, we use the open interval from -90 to 90 degrees. This chopping makes the inverse a true function, giving one clean answer. Let's find the sun's elevation. A 6-foot vertical pole casts a 10-foot shadow on flat ground. The pole is the opposite side to the sun's angle, and the shadow is the adjacent side. The tangent of the angle is opposite over adjacent, which is 6 over 10, or 0.6. To get the angle itself, we use the inverse tangent, arctan of 0.6. A calculator gives about 31 degrees. So the sun is roughly 31 degrees above the horizon. This same method works for any right triangle where you know two sides. Just identify the ratio, and apply the matching inverse trig function to find your angle. A trigonometric equation is just an equation where the unknown is an angle tucked inside a sine, cosine, or tangent. For example, sine of x equals 0.5. Unlike a regular equation where you get one number, here the angle can have infinitely many solutions because the trig functions repeat as you go around the circle again and again. Think of a clock hand. If I ask when is the hand pointing straight up, the answer is 12 o'clock, but also 12 o'clock tomorrow, and the day after. The pattern repeats every full turn. That's the core idea. We're finding all angles that make the statement true. Why do we care about finding every solution? Because the real world is full of things that go in cycles. A sound wave vibrates back and forth, the tide rises and falls, a swing goes to and fro. All of these are described by sine and cosine. If you're designing a bridge or tuning a musical instrument, you need to know exactly when the vibration hits a certain point, not just the first time. In calculus, when you solve problems about motion or waves, the math will spit out a trig equation, and you must be able to list all the angles that work, not just one. Missing solutions means missing real physical answers. Here's the step-by-step method. First, we isolate the trig function, like sine x equals a half. Then we find the principal angle, the one our calculator or the unit circle gives us. For sine of x equals a half, the principal value is pi over 6, or 30 degrees. But look at the unit circle, sine is the height, and there's another angle with the same height on the other side of the circle, which is pi minus pi over 6, or 5 pi over 6. That's the symmetry trig. Finally, because sine repeats every full turn of 2 pi, we add 2 pi n, where n is any integer, to both of those base angles. That gives the general solution x equals pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. The word the general just means it covers every possible answer. Let's solve a concrete problem. Imagine a Ferris wheel with a radius of 25 feet, and its center is 30 feet off the ground. It completes one full turn every 20 seconds. The height of a rider above the ground is given by the equation height equals 30 plus 25 times sine of pi t over 10, where t is time in seconds. We want to know, at what times is the rider exactly 50 feet high? First, set the equation to 50. Subtract 30 from both sides to get 25 sine of pi t over 10 equals 20. Divide by 25 to isolate the sine, sine of pi t over 10 equals 0.8. The principal angle whose sine is 0.8 is about 0.927 radians. The second angle in the same cycle is pi minus that, which is about 2.21 for radians. Imagine you're zooming in on a tiny slice of the unit circle, right near where the angle is 0. As the angle gets incredibly small, the curved arc and the straight vertical line of sine become almost identical. This is the heart of our first key limit. As theta approaches 0, sine theta divided by theta approaches 1. But here's the catch, this only works when theta is measured in radians, because radians are built from the arc length itself. Once you understand this one limit, you can figure out several others, like the limit of 1 minus cosine theta over theta, or tangent theta over theta. So why do we care about a limit at 0? Because it unlocks the derivative of sine. To find the slope of the sine curve at the very start, at x equals 0, we need to evaluate exactly this limit, sine of a tiny step divided by that tiny step. That slope turns out to be 1, which is cosine of 0. In fact, this limit is the key that proves the derivative of sine is cosine, and the derivative of cosine is negative sine. Without it, we couldn't do calculus on any wave, circular motion, or oscillation. It's the tiny hinge that the whole door of trigonometric calculus swings on. Let's derive why sine theta over theta goes to 1. Look at the unit circle with a small angle theta. We can trap the area of the pi slice sector between the areas of two triangles. The inner triangle has area half of sine theta. The sector area is half of theta because in radians the arc length is exactly theta. The outer triangle has area half of tangent theta. So we have half sine theta less than half theta less than half tangent theta. Multiply by 2 and divide by sine theta, and we get 1 is less than theta over sine theta is less than 1 over cosine theta. As theta shrinks to 0, cosine theta goes to 1, so theta over sine theta is squeezed to 1. Taking the reciprocal gives our limit. Let's use this limit to solve a concrete problem. Find the limit as x goes to 0 of sine of 3x divided by x. If we just plug in 0, we get 0 over 0, which is undefined. But we can rewrite the expression by multiplying and dividing by 3. That gives us 3 times sine of 3x over 3x. Now set theta equal to 3x. As x approaches 0, theta also approaches 0. So the fraction sine theta over theta goes to exactly 1. The whole limit is 3 times 1, which is 3. This trick of matching the angle inside sine with the denominator works for any constant multiple, like sine of 5x over x giving 5.